Welcome to lecture 6 of module 2. This is the lecture number 16 of the course. In the last class, we started discussing the celebrated James Cummings model. In this class, we will continue our discussion on James Cummings model. Apart from that, we are going to discuss a landmark experiment related to James Cummings model in the context of circuit quantum electrodynamics. So let us begin. In the previous lecture, we started discussing the famous Jaynes Cummings model, which described the interaction between a field mode and a two-level atom or system. In our case, the field mode is a microwave field in a transmission line resonator. So we have a microwave field in a transmission line resonator. On the other hand, the atom, the two-level atom, is nothing but a Cooper pair box. The first term in the Hamiltonian refers to the field mode energy. The second term refers to the two-level atom in the coupled to the resonator. And while this last term represents the interaction between the two-level atom and the field mode. In fact, the James Cummings model is pretty universal. It can even describe interaction of a natural atom placed inside a cavity. This natural atom can be modeled as a two-level system, and this interacts with an optical field. So this is our optical field, one optical field mode inside the cavity, and this is our two-level atom or system. Okay, and this can also be described using the James Cummings model, and in fact this is the domain of cavity quantum electrodynamics. And what we are discussing in this particular model is actually circuit quantum electrodynamics. So, but the James Cummings model can equally be utilized in other domain as well, such as cavity quantum electrodynamics. Now, this JC model or James Cummings model cannot be solved analytically. However, it can be solved under the so-called rotating wave approximation, and in the rotating wave approximation, the JC model can be written in this particular form, where instead of sigma x, we just replace it. We just, as we explained earlier, that if we break it up into say lowering operator or raising atomic operator and the lowering atomic operator, and when we multiply, we take the whole term because has to be multiplied with a plus a dagger. 4 terms should be there. Then out of these 4 terms, we are going to keep only 2 terms because of physical reasons, as I explained in the previous class. Now the label scheme based on this RWA James Cummings model we discussed. Here, as you see, that when their say coupling is 0, then we can have 2 kind of harmonic oscillator ladder depending on whether the atom is in the ground state or in the excited state, and what is the number of photons in the field mode. And we encountered an important parameter called the detuning parameter. On the other hand, when we go over to the case of coupling, when this coupling parameter is no longer 0, as well as if this coupling is very weak, then under rotating wave approximation we discussed this, only the neighboring energy levels matters, and we can ignore interaction between the far away energy levels, and therefore we can take the basis states to be like this, where either the atom is in the ground state with n number of photons in the field mode, or the atom is in the excited state with one less photon in the field mode. And the matrix element that connects these neighboring energy levels is was given worked out, and it was h cross z into the square root of n. And then we went on to discuss the matrix form of the RWA Jaynes Cummings Hamiltonian, and we worked out this matrix. And also we found out the eigenvalues of this matrix for this Jaynes Cummings Hamiltonian. And the resonant case we discussed at the end, and we found that this for the resonant case, that means when delta is equal to 0, we saw that this energy level gets splitted up into two, say as we see for this particular states here. Energy, this splitting is twice h cross z, and for this case we see that the energy levels get splitted by 2 root 2 into h cross z. This excited energy state here would be, from this expression you see, this would be twice h cross omega plus h cross z root 2, and on the other hand this one, it would be twice h cross omega minus h cross z root 2. So that's why the splitting is 2 into root 2 into s cross z. Okay, and that's where we actually concluded our class last time. Now what about the dynamics? Say at time t is equal to 0, the atom is in the ground state and there are n number of photons in the field mode. Then how the system will evolve in time? Let us say we prepare our the initial state of the system with the atom being in the ground state and there are n number of photons in the field mode. So this is what we have prepared at time t is equal to 0. So this is the state of the system. Now our goal is to find out what is the state at some arbitrary time t. It is easy, as we already know the eigenstates and their corresponding eigenvalues of the system, because we already discussed, say when we had our energy eigenvalue to be say E plus, which we worked out as h cross omega n plus h cross z square root of n. This corresponds to the eigenstate 1 by root 2. It's a symmetric superposition of this state where the atom is in the ground state and there are n number of photons in the field mode, or the atom is in the excited state and one less photon in the field mode. On the other hand, E minus correspond to h cross omega n minus h cross z square root of n, and the corresponding state is simply the antisymmetric superposition of these two states, which we already discussed. We can use these informations to find out what is our state vector at an arbitrary time t, and from elementary quantum mechanics it's easy to do. So we know that one state we have is 1 by root 2. So let me utilize this information. So let me write here again. We have this symmetric superposition state. This is the eigenstate, one of the eigenstate of the system, and the energy eigenvalue is E plus. So we have, as the state evolve, this is one part of the evolution, and another one is 1 by root 2. This is the this is the antisymmetric superposition of these two states, and this would be e to the power plus I by h cross E minus t. Now please note that if this is the correct expression, we should be able to get at time t is equal to 0, we should be able to recover our originally prepared state, that is the atom in the ground state, and there are n number of photons in the field mode. If you check it, we can recover it provided we just put here in the denominator square root of 2, and here if we put in the denominator square root of 2. So if you check it carefully, at time t is equal to 0, you will see this term and this term would get cancelled out, and then this term and this term will add up, and you will end up with the required state. Okay, so therefore let me write that we then obtain that at any arbitrary time the state of the system would be simply 1/2 this symmetric superposition. Here we have this, and here we have e to the power minus I by h cross e plus t plus half antisymmetric superposition of these two states. Okay, and here I have e to the power minus ih cross e minus t. So this is the state we obtain. Now the question is very easy actually to work out. What is the probability that you will find the atom in the ground state at a later time? So how you can work it out? What I want to do is this. The question is, suppose you were at an arbitrary state psi of t, and now you want to go to the state where the atom is in the ground state and n photons in the field mode. So what is the probability? We know from our elementary quantum mechanics, just we have to work out this particular quantity. Now psi of t we have worked out, so you just take the scalar product of psi of t with this state. So from this expression I think you can easily work out. So let us do it. So if you do that, you will immediately see that here inside this bracket you are going to get 2 here in the denominator, and in the numerator you will have e to the power minus I by h cross e plus t plus e to the power minus I by h cross e minus t mod square. And let me write it in a simpler form, 2 e to the power minus I say omega plus t plus e to the power minus I omega minus t mod square. Here omega plus minus is basically e plus minus by h cross. I'm writing both the expression just by using one equation. Now if I break it, I will have 1 by 4 because it is mod, so I have e to the power minus I omega plus t, e to the power minus I omega minus t here, into e to the power plus I omega plus t plus e to the power plus I omega minus t. So if you break it up, very simple, you are going to get 1 by 4. You will get simply I think you please do it, it's very simple. You will get 2 plus twice of cos omega plus minus omega minus t. Okay, this I can further simplify it as 1/2 1 plus cos omega plus minus omega minus t. Now you know that omega plus minus omega minus is nothing but e plus minus e minus by h cross, and that is equal to because we have already this expression, you just have to take the difference. So you are going to get here h cross will get cancelled out, and you will have 2z into square root of n. So finally you obtain this expression. The probability of getting the atom or the two-level system in the ground state would be given by 1/2 1 plus cosine of twice z root n into t. Okay, Now let me plot this probability versus time. Okay, let us plot it. So probability we are going to plot in the y-axis here, because it is probability. Minimum value should be 0 and the maximum it can attain is 1, and in the x-axis let us put time. So this is going to give a clear understanding of what's going on. So at time t is equal to 0, we have prepared our system in the ground state. The atom is in the ground state, so we'll start here, and later at some time t, this cosine term will become -1, so we'll have this probability to go, will go to 0. So we'll have it will go to 0. Okay, so when it go to 0, probability of getting the atom in the ground state is 0, means the atom is actually now in the excited state, and which means that one photon from the field mode is getting converted to one excitation in the atom. Now as time goes on, the excitation in the atom become a photon again, and the atom will again go to the ground state. Okay, so it will go to the ground state, and so as time goes on, you will get this behavior will repeat, and you will get oscillating behavior and oscillation, and this oscillation is known as the so-called Ravi oscillation. The frequency of this oscillation, so this is frequency of oscillation, is actually given by z into square root of n. Okay, now clearly as this n, the number of photons in the field mode, is getting larger, the oscillation will go faster. So if n is very large, so you will get oscillation will also become rapid or very fast. Okay, in fact this quantity z into root n, square root of n, play the role of Ravi frequency or field amplitude. So z into root n, this is called Ravi frequency. As we discussed in the first module, this is related to the field amplitude. So as you know, for very large n, if n is much greater than 1, for very large n, we actually go over to the classical regime, classical driving field. The driving becomes classical, so we can consider the driving field to be classical in nature. On the other hand, there is another limit at the other side. In the extreme cases, say when n is equal to 1, that means you have only one photon in the field mode, then in that case, as you see from these expressions here, either we are going to have actually two states. Either we are going to have the atom in the ground state and there is one photon in the field mode, or we are going to have atom in the excited state and there would be no field mode. These would be the eigenstates, and therefore the oscillations will occur between this particular state and this state, where this state is interesting because you see there is no photon in the field mode, and that is the so-called vacuum. And when n is equal to 1, in this case the Ravi oscillation is basically taking place between one photon state of the field and vacuum state of the field. So that's why this oscillation for the n is equal to 1 case is known as vacuum Ravi oscillations. Vacuum Ravi oscillations. Okay, now this vacuum Ravi oscillation has no classical counterpart. It is a quantum mechanical phenomenon. Let us consider another important situation when the detuning parameter is very large, means when the detuning parameter delta, which we defined as omega atom minus omega atom is the atomic transition frequency and omega is the field frequency, and we are going to consider the situation when this detuning parameter is very large than the coupling strength between the atom and the field. So this is actually a very useful case. We'll see that in this regime, when the detuning parameter is very large than the coupling strength, the frequency of the field mode will turn out to depend on the state of the atom, and this actually imply that we can determine the state of the atom just by measuring the frequency of the field without directly making any measurement on the atom. This case, when this detuning parameter delta is much greater than Z coupling strength, this case is called dispersive case. This is called dispersive case. We'll now analyze it in somewhat details. Now we know that within the rotating wave approximation, the Jaynes-Cummings Hamiltonian in the matrix form, we wrote it already under RWA. It was H cross omega n here, and here it is H cross omega n plus H cross delta, and the off diagonal elements were H cross z square root of n, H cross z square root of n. Just recall that we wrote this Hamiltonian in the basis atom in the ground state with n number of photons in the field mode and atom in the excited state and one less photon in the field mode. So these were the basis states. Now also we worked out the energy eigenvalues of this matrix. So it was E plus minus is equal to H cross omega n plus H cross delta by 2 plus minus H cross square root of z square n plus delta by 2 whole square. Now let us assume, as we are considering the dispersive case, say the detuning is much greater than the coupling parameter. Remember that delta is equal to omega atom minus omega, so it can be greater than 0 or it can be less than 0, but for our calculational simplicity, we are going to consider delta greater than 0. So in this case, when coupling parameter detuning is much greater than 0 z, let me now, in that regime, let me expand this expression under the square root here. So let me just see how I can write it. Z square n delta by 2 whole square, because delta this is much larger than this quantity. So let me pull it out, and if I pull it out, then I have delta by 2 here, and I can write it, let me just put mod, because delta can be less than 0 or greater than 0. Then I have here 1 plus z square n divided by delta by 2 whole square. Okay, now I can write, because now this term is smaller than 1, so I can do a Taylor series expansion, and I can write this actually binomial expansion I can do. So I have 1 plus half, and you will have 4 z square n by delta square, and then you will have all higher order terms would be there. But as you will see, because of the condition that we are having, all the higher order terms we can neglect to a good approximation. Then we'll have the first term would be mod delta by 2 plus z square n by mod delta, and then we have here all the higher order terms in z square by delta. Okay, so now as I said, for simplicity we are going to take delta is greater than 0, this determining parameter. Then I can write my new energy level E plus minus. I just have to put this expression, put this form here. So if I put it there, then I will get my, let me write it very clearly here, I will get E plus minus is equal to h cross omega n plus h cross delta by 2 plus minus h cross, and then this, which is what I am going to have, delta plus 2 z square n by delta. So if I break it up, I get two energy values. One is E plus and another one is E minus, and E plus will correspond to h cross omega n plus, because of this plus sign these two terms will add up, so I will have h cross delta and I will have h cross z square n by delta. On the other hand, I will have here h cross omega n minus h cross z square n by delta. Okay, in fact let me rewrite it. This I can also write in this form. Say E plus is equal to h cross omega plus z square by delta into n plus h cross delta, and E minus I have simply h cross omega minus z square by delta n. Okay, so clearly if you look at these two expressions here, you see in reality we are now having, in this dispersive regime, we are having two ladders of harmonic oscillator levels which are equally spaced. In one case the spacing is given by omega plus z square by delta, because you see this is related to the field mode, right? And you know that field mode is act like a harmonic oscillator. And now what I'm saying is that we have two harmonic oscillator where, because this is related to field, we are having two harmonic oscillator and their spacing frequency all, and you know that the harmonic oscillators have equal spacing in the energy level. So spacing here is, in one case it is given by omega plus z square by delta, in another case it is given by omega minus z square by delta. So now actually it depends on the state of the atom. As you know that E plus refers to the case when the atom is in the excited state, while E minus refers to the case when the atom is in the ground state. So actually you can recall that when we considered the case where z is equal to 0, let us just recall that when we discussed the case z is equal to 0, we had E plus is equal to h cross omega n plus h cross delta, who is, in fact, if you remember, we can write it as h cross omega n minus 1 plus h cross omega atom here. So the atom is in the excited state, and in the field there are n minus 1 number of photons where they are in the field mode. On the other hand, we had another energy level that was simply h cross omega n. Now here n photons are in the field and the atom is in this case the atom is in the ground state. Atom is in the down state or in the ground state. Okay, this we already know. So keeping these things in mind, so from, let me once again write, from E plus is equal to h cross omega plus z square by delta, okay, n plus h cross delta, and E minus is equal to h cross omega minus z square by delta n. What we can find is that in the dispersive case, when z is not equal to 0 and this detuning is much greater than this coupling parameter, the field mode frequency, as you can see from these two expression, let me write here, the field mode frequency. Now you see clearly that it depends on the state of the atom, okay. This is an important result, because earlier, say, when there is no coupling, nothing else was there, suppose the field frequency was omega. Now because of the coupling and when the detuning is very large, so now the field frequency becomes omega plus minus z square by delta, okay. So here this plus sign, plus refers to atom in the excited state. So atom in the excited state, what it means is that if you make a spectroscopic measurement, suppose you measure the field frequency, if you find the field frequency to be larger because of the plus sign than the original field frequency omega, then you will automatically know that the atom is in the excited state. On the other hand, the minus case, the lower case, refers to the fact that the atom is in the ground state, okay. That means if you make the spectroscopic measurement, that means you make the measurement of the field frequency, then if the field frequency is lower than the original frequency of the field mode, then you will automatically know that the atom is in the ground state. So this is actually a very useful tool to determine the state of the atom without making any measurement directly on the atom. It's a very useful spectroscopic tool, and it is nowadays routinely used in circuit quantum electrodynamics. Now all these effects that we discuss for the dispersive case could be summarized in the form of an effective Hamiltonian. In order to write the effective Hamiltonian, let us use this sigma z is equal to, say, plus 1. This is the z component of the Pauli matrices. Let us say sigma z is equal to plus 1 refer to the atom in the ground state and with n minus 1 number of photons in the field mode, while sigma z is equal to minus 1 refer to, actually the eigenvalue of sigma z, it is either it has two eigenvalues, plus 1 and minus 1. So I am writing that plus 1 refers to the case when the atom is in the excited state and there are one less photon in the field mode, that means n minus 1 number of photons in the field mode. On the other hand, when eigenvalue of sigma z is equal to minus 1, we have the atom in the ground state and there are n number of photons in the field mode. So then we can write an effective Hamiltonian for the system for the dispersive case. So we can write an effective Hamiltonian, and we are writing it for this dispersive case. Now you recall that earlier what we had for the field mode in the Jaynes-Cummings model, in the field mode we have this field frequency is h cross omega, and then we had this a dagger a was there. Now because as you see the field frequency now starts depending on the state of the atom, to incorporate that we have to put this field frequency as we have here. From here you see, because of this we have to write it as, in the operator form we can write it z square by delta. Okay, let me write it this way, and then sigma z. So this we have an operator here, and then we have this a dagger a, which represents the photon number. On the other hand, for the atom case, again from the Jaynes-Cummings model we know that in the case of the atom we had this, and we had this term sigma z plus 1 by 2, where if sigma z is equal to 1, then we know that we have h cross omega atom, that means the atom is in the excited state, and if sigma z is equal to minus 1, then the atom is in the ground state. Now to get the correct energy values that we have worked out here, you have to add, you can actually verify it, you have to add this term here z square by delta, then you are going to get the correct energy eigenvalues for the system. So this is the effective Hamiltonian for the model in the dispersive case. In fact, this Hamiltonian could be written in some other different form as well, but I will not go into those models or those form of the Hamiltonian. And now I think it's time for us to discuss some experimental work regarding this Jaynes-Cummings model in the context of circuit QED. So let us study, or actually just discuss some landmark work regarding experiments on the Jaynes-Cummings model in circuit quantum electrodynamics. The standard setup for circuit quantum electrodynamics, which we already discussed earlier, is as follows. We have a transmission line resonator. We know how to get a transmission line resonator. Suppose we have a transmission line, infinite transmission line, then we break it at two locations, and then we get a transmission line resonator. And then we have a Cooper pair box or a two-level system which is getting coupled to the transmission line resonator at some location, and the coupling strength between the transmission line resonator and this Cooper pair box is dependent on the location that where the Cooper pair box is put on the transmission line, and this thing we discussed earlier. In fact, so far I discussed about only one type of two-level system, two-level artificial system. So in the next class I'm going to discuss about some other kind of two-level artificial system which is routinely used in circuit quantum electrodynamics experiments or setup. Now anyhow, at the moment let us discuss, say we have a Cooper pair box that is put on the transmission line resonator like this. Now what is done is a microwave drive signal is incident on the transmission line resonator or the system here like this, and this microwave signal gets some part of the microwave signal that is incident on the resonator is getting transmitted. It's get transmitted, and a part of the signal here may also get reflected. And what is done in experiment is that by looking at the intensity of this transmitted beam, the people infer, the experimentalists infer about the state of the Cooper pair box or the two-level atom, and other things about the system. In fact, this scheme was experimentally realized in laboratory by a Yale group long back in 2004, and it is considered to be an landmark experiment in the area. And this was published in the journal Nature. The title of the article was this: strong coupling of a single photon to a superconducting qubit using circuit quantum electrodynamics. So it was the Yale group, and one person was actually associated with Indiana University as well. So it's primarily it was done in Yale, and this was published in the journal Nature. And it may be useful to read the very insightful abstract of the paper. Let us read it. It says, the interaction of matter and light is one of the fundamental processes occurring in nature, and its most elementary form is realized when a single atom interacts with a single photon. Reaching this regime has been a major focus of research in atomic physics and quantum optics for several decades, and has generated the field of cavity quantum electrodynamics. Here we perform an experiment in which a superconducting two-level system playing the role of an artificial atom is coupled to an on-chip cavity consisting of a superconducting transmission line resonator. We show that the strong coupling regime can be attained in a solid state system, and we experimentally observe the coherent interaction of a superconducting two-level system with a single microwave photon. The concept of circuit quantum electrodynamics opens many new possibilities for studying the strong interaction of light and matter. This system can also be exploited for quantum information processing and quantum communication, and may lead to new approaches for single photon generation and detection. So this is a very important work, and the experimental real transmission line resonator and the Cooper pair box is actually shown in this diagram. I would not go into the details. Actually, what you see here, it is the input end of the transmission line resonator, and this is the output end here, and in middle here this Cooper pair box is placed. I would like to encourage interested people to read the article for experimental details and fabrication. Actually, this on-chip cavity that is shown here is made by patterning a thin superconducting niobium film deposited on a silicon chip. And you may go to read the article for the experimental details and also about the fabrication. So the essence and the idea of the experiment is already I have described. So in essence, this is basically this is the setup, or this is the scheme, as I already explained. What I will do now is that I will try to explain the key findings of this landmark paper based on what we have learned so far. Now, what the group observed was the intensity of the transmitted beam. They plotted the intensity of the transmitted beam as a function of the drive frequency. So in the y-axis they plotted the transmitted intensity of the signal or the beam. Here the transmitted intensity, and it was plotted as a function of the frequency of the weak oscillating microwave drive. Let me just again explain what I actually telling you. You remember essentially the experiment the scheme is like this. We have this transmission line resonator is there, and this transmission line resonator is getting coupled to a Cooper pair box placed somewhere here, say, and a microwave and weak oscillating microwave drive is incident on the transmission line resonator. Then a part of the microwave is getting transmitted, and a part of it is getting, say, reflected. So this is the scheme. And what they observed, they basically measured the intensity of this transmitted beam, and when they did the experiment, first of all they observed that when there is no Cooper pair box or the qubit, they observed one single peak like this. So this is without the Cooper pair box or two-level atom, or now onwards we can also say it to be qubit, because ultimately qubit is nothing but a two-level system, and this is one of the important application that they had in mind, as you have read in the abstract, that they are quantum information processing. So now onwards let me tell two-level atom or Cooper pair box simply as qubit. So this is what they had without this qubit. And by the way, once we have a setup like this, or we have done the fabrication, we cannot get rid of the Cooper pair box, right? But then how they got it, this result? It can be done if we detune the qubit or detune the drive frequency from the atomic transition frequency significantly, then the influence of the qubit would no longer be there. So when I say that without qubit or Cooper pair box, I mean to say that it is actually without having it influence. Now when this drive frequency matches the atomic transition frequency, that means when delta, detuning parameter delta, is equal to 0, so what they observed is they observed two peaks. They observed two peaks instead of this single peak. So, and this is the case when detuning is equal to 0. Okay, and the spacing between these two peaks was found to be 2 into z, where z is the coupling strength between the microwave Cooper pair box and the microwave signal, right? So this is what they observed experimentally. Now we'll try to understand this particular result. So the question is, in fact, let me, before we try to understand it, let me give you the experimental, what they in the experiment. You see here in this first plot, they first observed the only single peak when this qubit is heavily detuned. That means when it had no influence, as I explained already, and when in the detuned case, when delta is equal to 0, they observe these two peaks. Okay, let us now try to understand actually what is going on. So the question that we have to ask is, at what frequency omega, at what frequency omega of the omega drive, a microwave photon can enter, a microwave photon can enter into the resonator and thereby excite the atom there, okay, or the qubit. So clearly that can happen only if when this frequency matches this atomic transition frequency that we know from elementary quantum mechanics. So the point is that initially what we had, initial state of our system is the atom is prepared in the ground state and there is no field, there no photon on the field mode. So this is what we have initial, this is our initial state. And then finally what we had is that we had a final state. I will discuss about it, what it is, because in the now in the final state, obviously what we have one photon is getting created inside the system. So this initial state and the final state is basically connected by a creation of a photon inside the system. And this matrix element, just for our understanding, I'm writing it like this. So it means that this matrix element connecting the initial state and the final state, which are connected by the creation of a photon inside the system, is no longer zero. And let us understand, this can be now very well understood, the origin of these two peaks, just by going back to our Jaynes Cummings model level scheme. So you recall that what we had in the Jaynes Cummings model, the atom initially is in the ground state and there is no photon in the field mode, and we had this excited state here, energy state, when atom is in the ground state and the one photon in the field. Or when at resonance we have this situation, the atom may be in the excited state and there is no field photon, but because of the coupling between the atom and the qubit or the microwave field, these degenerate states become non-degenerate, they become hybridized, and we have these two energy levels, and this splitting happens. And this splitting, as we already discussed, is equal to twice h cross z, right? And where z is the coupling between the microwave field in the qubit or the atom. And this particular energy state is simply a superposition of this state and this state, symmetric superposition. We have this symmetric superposition of these two states. On the other hand, this particular state is a antisymmetric superposition of atom in the ground state, one photon in the field mode, and atom in the excited state, no photon in the field mode, right? This is what we have. Now, as I said, that we have a photon is getting created inside the system. So if you look at these two hybridized state here, this state as well as this, you will observe that in both this contribution, while we started with no photon initially, now here we have one photon, a contribution is there, similarly a contribution is there. So clearly two transitions are possible. One transition would be this one and another transition would be this one, right? And therefore we can say from this, it is easy to see what is the reason behind observing these two peaks. Okay, this is the reason. Because of these two possible transitions, we get two peaks. Another study the group did was to change the detuning parameter delta by changing the atomic transition frequency. By the way, here these results that is plotted is for detuning parameter delta to be equal to 0, and as you remember that delta is equal to omega atom transition frequency of the atom minus the bare cavity frequency. And once we fabricate the system, actually this bare cavity frequency small omega gets fixed, and only option that we have, if we want to change this detuning parameter, we have to change the atomic transition frequency. Now because we are using Cooper pair box or artificial atom, so this changing this atomic transition frequency is easy. We just have to change this Josephson coupling energy here, easy, and that can be done by changing the gate voltage or the gate charge. So what is done is that in one axis we can just plot this. We have this detuning parameter, while in the another axis, that is in the say y axis, here y axis we have this omega drive, that is the driving frequency of the microwave. So now say delta is equal to 0 is somewhere here. As we already know, at delta is equal to 0, as you can also see from this plot here, the omega drive, we have two peaks, so omega drive has two values here, and we have two peaks at 2 points. So we have one peak here, and say we have another peak is here, right? And let us say our bare cavity frequency, which is fixed, that is equal to omega. This is the bare cavity frequency, and we are, as we are, the detuning parameter is getting changed, we just have to change the atomic transition frequency, and that is something like this. So this is what our omega atomic, that's how it is, atomic transition frequency is getting changed, and this is the point of crossing or the degeneracy point, where omega is equal to, this bare cavity frequency is equal to omega atomic frequency, or the drive frequency is exactly equal to the omega here, and this is the point, and this difference is, as we know, that is equal to twice z. Now when the coupling is there, when z is not equal to 0, these energy levels no longer cross, and we have these bare energies here, and here also we have these bare energy levels are there, and we encounter what is called avoided crossing, right? Let me draw it properly. So what we encounter is called atomic avoided crossing, and this already we discussed in great details in module 1, as well as here, as you see, in the context of James Cummings model, this is observed in the Yale group's experiment. They have experimentally demonstrated this kind of behavior. Okay, another issue that we can discuss is, what about the intensity of these peaks? Now when delta is equal to 0, that means at the detuning, this peak intensity is actually related to, as I discussed earlier, this is related to this matrix element connecting the initial state and the final state, and that is connected by generation of a, or excitation of a photon inside the cavity. Now as we discussed earlier, that this is the situation when the contribution, I think here we discussed it, yes, here we discussed it, the contribution is when a photon is, we have actually started with no photon in the field mode, and now a photon is created inside it. Contribution is because of this term as well as this term, and both these terms has this equal weightage 1 by root 2. So when delta is equal to 0, the intensity would be actually the same here, and both the peak would have the same intensity. But the question is that what happens if we go away from this detuning parameter, or detuning delta is equal to 0? The answer is simple here, because you see what we are going to have here, as suppose we are, our omega drive frequency is here, that is exactly equal to the atomic transition frequency, but at this point you see we are away from this bare cavity, that means there is no photon inside here, inside the system. So intensity, the matrix element, this would be equal to, nearly would be equal to 0, right? So it would be the situation here. So on the other hand, if we are at this end, when our omega drive is nearly equal to omega, then there would be a generation of photon inside the cavity. So we'll have, this would be non-zero, we'll have a finite contribution from here, so there will be intensity. Similar argument goes to this point. So you will get a intensity would be high here near the bare cavity frequency when omega drive is equal to bare this frequency, bare cavity frequency. Similar is the case here. It will go, the intensity would be high up to this point. Then as we go away from this point, intensity would get lower and lower. Okay, I hope this point is clear. So this is what is observed experimentally as well. Now another thing is that what about the dispersive case that we discussed? As you see from this plot as well as this plot, the dispersive cases, we are away from the detuning. So here you see this omega drive frequency, that is your omega drive, is actually not exactly matching the bare cavity frequency, and that is different from the bare cavity frequency by omega is by z square by delta. That is what we discussed. And here also the same thing, that is also given by omega dash is equal to omega minus z square by delta, because of the fact that we always start, you see this minus sign refer to the fact that the atom is actually in the ground state, and that's what we always start, right? In this experiment, the atom or the qubit is always in the ground state. Now in this case, because delta is less than 0 in this part here, I'm talking about this part, so your omega dash is greater than omega because delta is less than 0, and in this case you have omega dash is greater than it would be smaller than omega, as you can actually see from the diagram. Also omega dash is equal to omega bare cavity frequency because delta is greater than 0. So all these things you see as per our model, everything, all the experimental results is very nicely explained by the analysis that we did with the Jaynes Cummings model. Let me stop for today. In this class we completed our discussion on Jaynes Cummings model, and we saw how we can understand the experimental results obtained by the Yale group based on our discussion on Jaynes Cummings model. Now, so far we have not discussed much about Josephson junctions, and this is what we are going to take up in the next class. We are going to discuss in somewhat details about Josephson junctions in the next class. So, see you in the next class. Thank you.